Okay, let me start. So these are the topics that we need to talk about today and possibly the next lecture. And as I promised, after this, we will be dealing with relatively more concrete things, in particular matrices. But this is somewhat abstract, and I want to do it carefully. So sometimes it will look as if I'm being a bit too careful, unnecessarily careful, and maybe that is the case. In my effort to be precise, so I make a fuss sometimes. Okay, so one of the things is I like to keep a distinction between a set and an ordered set, and in fact there is a third related concept, namely a finite sequence of elements in a set. So supposing I have a set X, and then I have a subset of elements. Okay, so elements would be X, Y, Z, and some n element, some n elements of X. So this is just a subset of X, and clearly this is just a way of listing the elements in the subset. So as a subset, this is the same thing as Y, X, Z, etc. Except that when I list these it's understood these are distinct elements, n distinct elements. Okay, so this is called a subset of with n elements. Okay, so let me call this Y. Y is a subset of X with n distinct elements. And you note that in this case, I am using these curly brackets so then the elements of the set are put between curly brackets, and it doesn't matter in which order I put them. On the other hand, there is a notion of ordered subset. So if I take the same set and list the elements in some order, so I declare that this element comes first, this element comes second. So what is that? This is a bijection between the set 1, 2, 3, n and 1. Okay, so to get an ordered subset, and then if one goes to X, 2 goes to Z, 3 goes to Y, etc., then I will write X, Z, Y with the round bracket as the ordered set. So this is unordered set. Unordered set. This is the ordered set. Okay. So, but note that this is a bijection. So distinct integers between 1 and 2 go to distinct elements of Y. And the third related notion is a sequence of n elements in X. Okay, so that would be a map from the set 1, 2, 3, n to X. So then one will go to some element, 2 will go to some element, but these need not be distinct. Okay. So these are three different things: a subset of X consisting of n elements, an ordered subset of X with n elements, and a sequence of n elements in X. These are three distinct things. A sequence is a map from the set 1 to n to X. An ordered subset with n elements is a bijective map from the set 1 to n to X. And a subset with n elements is just the subset without any order in them. Okay. So why am I making this fuss at this point? Because when it comes to notions of linear independence, bases, etc., the normal practice in linear algebra is to actually work with ordered subsets, make all the definitions, and then they say that the concept does not change if I change the order. So if an ordered subset is linearly independent, any change in the ordering will give you another linearly independent subset. Okay, so it's clear then that the notion of linearly independent subset is really a notion that applies to unordered subsets. So, and I have tried to make my exposition in a way that that makes this clear. Okay, in some cases maybe this only confuses you, in which case you can go to the more traditional accounts, and the important thing is you should understand the underlying idea. Okay, and I say more about this business about ordering in the notes because it's something that for some reason irritates me, and so I like to be clear about this. Very good. So now we are dealing with we have defined linear independence. Let me just find my notes. Give me a minute. So recall, given subset S of a vector space V, we say that S is linearly independent if the following holds. Given distinct vectors, m distinct vectors with n bigger than or equal to 1, distinct non-zero vectors, given a subset S, if of non-zero vectors. So first of all, we demand that the elements of S are non-zero vectors. In S, V1, Vm, and scalars lambda 1, lambda 2, lambda m. The equation lambda 1 v1 plus lambda 2 v2 plus lambda m vm equal to 0 vector holds if and only if lambda 1 is 0, lambda 2 equal to 0, lambda m equal to 0. So this is the definition of a linearly independent subset of a vector space. Note that the definition does not require S to be a finite set. It is some subset of of the vector space consisting of non-zero vectors. So none of the vectors in the subset is the zero vector. But so this set has a property of being linearly independent if whenever I'm given a finite non-empty collection of vectors in the subset and a relation between them, so that some scalars lambda1 to lambda n, so that the sum of these lambda1 times e1 equal to 0, this holds if and only if each of the scalars is 0. That is, without each of the scalars being 0, I cannot achieve this. So in the last lecture, I immediately began to prove various abstract theorems without pausing to talk about examples. But let us spend a little time with the definition. So we already saw that if S is the singleton set, so there is only one vector V which is non-zero, then this is linearly independent set. So I'm not going to go through that proof again. Now, let us take R2 example. R2. I'll give you 3 sets of vectors in R2, and you have to tell me. So let me create some space for myself. Examples in R2. Just give me a second. Okay. Okay, so I actually given you four subsets of R2, finite subsets. So in the here there is the subset consists of one vector. Here it consists of 2 vectors, both along the x-axis. Here it consists of 2 vectors, one along the x-axis and one along the y-axis. And here you see there are 3 vectors, one along the diagonal. Yeah. Now, let us apply our definition and ask which of these, if any, is a linearly independent subset. So again, for some of you who have the intuition or have experience with vector spaces, this must be clear. But for others, I want you to look at our definition and just take our definition of linearly independence and ask yourself which of these is linearly independent, decide, and then be ready to justify your answer. So I'll give you a little time to think. Is the question clear to everyone? I've taken the vector space to be R2, okay, which is the set consists of, according to our definition, it consists of tuples of pairs of real numbers, usually denoted by x, comma, y. And I've given you 4 examples of subsets of R2. The subsets in each case, the first subset consists of one non-zero vector. In the second subset consists of 2 non-zero vectors, both in the x-axis. The third subset consists of, I'm going clockwise, consists of 2 non-zero vectors, one pointing along the x-axis, one pointing along the y-axis. And the third subset consists of 3 vectors, one pointing along the x-axis, one pointing along the y-axis, and the third pointing along the diagonal. And what you have to ask yourself is, which of these 3 subsets is linearly independent and which of them is not? And then what I'm asking you to do is take my definition and apply it sort of word by word. So you may have other definitions in mind, you may have other intuition, but no, I want you to kind of get rid of your previous intuition and definitions. I want you to apply the definition that we have just seen.
The singleton vector and the orthogonal vector.
Wait. Wait. No, let everybody have time to think.
Excuse me, sir.
Yes.
So in the third diagram, the V3 is in the 45-degree angle.
Sorry.
So in the third diagram, the V3, what is the angle? Can you? Is it?
Okay, I will actually. Okay, I thought it was kind of clear. So let me just give you, each vector algebraically, so that there is no confusion. This is the vector 1, 0. This is the vector 1, 0. This is the vector minus 1, 0. This is the vector 1, 0. This is the vector 0, 1, 1, 0, 0, 1, and 1, 1. Okay.
Yes, sir, it's fine.
I hope everybody has signed into the chat. I see. Yeah. Okay. So now, let me see if there are any questions or comments in the chat. If anybody has any issues with this question and is too shy to ask, they can type a question in my privately to me.
Sir, I just kind of wanted to remind you that at the end of last class, you made us write a theorem, which was that if I have a spanning set of some vector space, then I can reduce it to a linearly independent spanning set.
Yeah. We have to get back to that.
Okay. I just want to remind.
Yeah. No, I know that there is a lot of unfinished business. So we have, but I didn't want to go very fast before, because this linearly independent thing is, yeah, we'll get back to that.
Okay.
Yeah. So there's some confusion. So let me even number the things properly so that if just 1 second. This is 1, 2, 3, 4. I'm going clockwise. So okay, so we've had enough time to think. So let me give the answer. Okay. So I'm going to be I'm going to go very slowly so that everybody follows. 1. V1 is linearly independent because we already noted that in any vector space, a singleton V1 non-zero is linearly independent. Okay, so this is a special case. Now, in the case of 2, you have V2. V2 is -1, 0. This is the definition. Is -1, the scalar -1 times 1, 0, which is -1 times V1. So 1 times V2 plus sorry. One times V1 is 0. So which contradicts linear independence. In the case of 3, if lambda1 V1 plus lambda2 V2 is a 0 vector, this means this is lambda1 times 1, 0 plus lambda2 times 0, 1, which is lambda1 0 plus 0 lambda2, which is lambda1 lambda2. And this, what is the 0 vector? It is 0, 0. So if this is 0, 0, lambda1 is 0, lambda2 equals 0, implies linear independence. In the case of 4, V3 is V1 plus V2, so that V1 plus V2, 1 times V1 times 1 times V2 plus -1 times V3 is 0, which so not independent. Okay, so we have methodically applied our definition and checked that 1 and 3 are linearly independent subsets, and 2 and 4 are not. Okay, can I go on? Note that we have not yet dealt with the notion of basis. So those of you who heard basis, we have not yet come to the notion of a basis. We are still trying to understand linear independence. But there is something that you can begin to think about, that in R2, we have found linearly independent subset consisting of one element, and we have also exhibited a linearly independent set consisting of two elements. But I would, well, if you think about it, try and find a linear independent subset consisting of three elements. Well, this set that I presented in example 4 is not linearly independent, but maybe if you are very clever, you can find another linearly independent subset of R2 with 3 elements. Okay, so you can play around, and in fact, you will not be able to do it. Okay, so that tells you that there is something special about R2, that the maximum number of linearly independent maximum size of a linear independent subset seems to be 2, and so this is what we will try to make precise during the rest of the lecture. Very good. So now let us resume the main thread of our lecture is that, so let us resume study of linear independent subsets. So I had stated this theorem. So we are dealing with V and vector space and S non-empty and finite. So this applies to this theorem and the next. I'm going to state two theorems. The second will be a slight strengthening of the first. So, theorem: if S generates V, i.e. span of S is V, there exists S prime contained in S, which is linearly independent, such that S prime generates V. So if I have a finite set of non-zero vectors that generates a vector space, whose span is the vector space, I can extract from within this set a subset, which could be all of S, because S itself could be linearly independent. But if S is not linearly independent, I can find a subset which spans V, which is linearly independent. Okay. So this we will prove. In fact, we will prove a strengthening theorem, stronger, which will imply this. If S generates V, i.e. span of S is V, and S prime, S tilde contained in S is linearly independent, then there exists S prime containing S tilde and contained in S, which is linearly independent, and S prime generates V. So this is strengthening because, okay.
Sir, what did you write as the subset of S? So I mean the tilde one. That.
Yeah. Sorry for the terrible writing. Then there exists, the exists applies to this. So we will come to theorem. So let me call this theorem tilde. So theorem tilde is a strengthening of theorem, because as I explained in the notes, it's very easy to go from here to here. So what does theorem tilde says? So supposing I have a finite set of non-zero vectors that generates a vector space, and which is not linearly independent, then, but supposing there is a subset S tilde of S, which actually is linearly independent, then I can expand S tilde to a subset of S, which has both properties, that that subset S prime on one hand spans V and is linearly independent. Okay, so this is actually, I mean, the statement and understanding the theorem is takes you more CPU time than actually writing down a proof. But you should understand the theorem, and you should see these things should be kind of integrated into your ways of thinking about vector space. It automatically, you know, you should know this. I mean, these are not things that you remember, oh, there's some strange result, etc. I mean, because that way, it should be part of your intuition about vector spaces that if I have a vector space that's generated by a finite set of non-zero vectors, I can extract a subset which generates a vector space and is linearly independent, because these are very special subsets. Subsets which are linearly independent and generate a vector space are precisely what we will call a basis. One such subset is called a basis. And if you have many, the point is a basis need not be unique. A vector space will have many bases. Okay. Okay. So now do you understand?
One doubt, sir.
Very good. Very good. Very good. So
Sir, could you state the difference between theorem tilde and theorem?
Yes. You tell me the difference. There is a difference because theorem doesn't talk about S tilde at all, right?
Yeah, exactly. So I don't understand what S tilde is doing there.
That is so this is part of the hypothesis. Until here is the hypothesis, and then here the conclusion starts here, and here the conclusion starts here.
Oh,
okay. Is that clear?
I'm thinking, sir.
Yeah, very good. Yeah, it's
Yes, sir, I got it.
okay. Anybody else? So in theorem tilde, I'm taking a finite generating set S, and I'm also given, somehow I managed to find some subset of S, which I called S tilde, which is actually linearly independent. See, if we were trying to, yeah, but then what theorem tilde says is that I can keep these guys and add on more vectors so that I get S prime, which spans V and is linearly independent. Okay.
Sir.
Yeah.
Sir, S prime in both theorem 1 and theorem tilde are referring to the both same family of subsets S dash.
They are all subsets of S. S prime is some subset of S.
Yeah, so
oh, wait, I think I've been too cryptic here. Let me just write this explicitly. Then there exists a subset S prime of S such that 1 S prime is V, S prime is linearly independent, and S prime contains S tilde. So in the first theorem, I did not start with the S tilde. In the second theorem, I start with some S tilde, which is linearly independent subset of S, and I'm declaring that, in fact, I can keep S tilde and add on more vectors. I can keep adding vectors from S, so that I end up finally with a set that spans V and is linearly independent.
So can't we just go from theorem 1 to theorem 2 by observing that?
Yeah.
By observing that every set has a singleton subset.
Sorry.
I mean, if there's an S.
I cannot hear you very clearly. There is some.
What I'm trying to say is that. So am I audible now?
No, there is some noise. I think there
background
is.
noise.
Yeah. When you speak, it's not. You are not clearly audible. Do you want to type your this thing? So I'm waiting for Romit Roy Chowdhury to type a question. In the meanwhile, if anybody else has something to say, you're welcome. Romit, are you?
Yes, I'm on my way.
You mind if we deal with?
So you can continue.
Yeah. Okay, so let me give the proof of theorem tilde. Now, if all the vectors in S set minus S tilde belong to the span of S tilde, then span of S tilde is span of S, which is V. So we can take S prime equal to S tilde. If not, there exists a V tilde 1, which belongs to S minus span of S tilde. Then S tilde union V tilde 1 is linearly independent. So let me call this S tilde 1. So we have now S tilde contained in S tilde 1 contained in S, and this is linearly independent by assumption, and this is linearly independent by construction. And we can continue like this. We can iterate the process, and this process must terminate because S is a finite set. This can be continued and must terminate. And this will give us S prime. So here we have used the result that we stated and proved in the last lecture, that if I have a linearly independent set and one vector that belongs to the complement of the span, then I can add that vector to the set, and the bigger set will be linearly independent. We have used that here. So this proves theorem tilde, and the theorem follows from theorem tilde in an essentially easy way, which I've denoted in the notes. So having gotten here, so let me see if so Romit, question is, can't we no, see, the point is, you see, Romit, the point is that it's not that there exists S tilde is not part of the conclusion. It is part of the assumption.
I mean, it's an assumption.
There is an S which is generates V, and I am given some subset S tilde which is linearly independent. It could consist of 5 elements, but the point is I can keep S tilde as it is and add on more vectors, so to get this span of V and also have linear independence. So theorem tilde is a stronger statement than theorem, which is why I'm proving theorem tilde and leaving theorem. Exactly. Theorem tilde is the stronger theorem. Think about it. Maybe I'm not this might be a okay. Let us give an example. Okay, here is an example.
So my question simply was,
yeah. So let me give you an example of the application of theorem tilde, and then let us see if this helps you. Yeah, Romit, can I do that?
Yes, sir, please go.
Yeah. So take V to be R3. And V1 is 1, 0, 0. V2 is 0, 1, 0. V3 is 0, 0, 1. And V4 is 1, 1, 1. Okay. Now I take S to be V1, V2, V3, V4, and I take S tilde to be V1, V2. So now, what is the span of S? That's R3. Do you see this? What is the symbol between S and S tilde in the proof? Where in the proof? Shakti, can I just remember to, okay, so I know I'm responding to 2 questions. I can complete my example or respond to Shakti's question. Let me respond to his question. What is the symbol between S and S tilde in the proof? So where are you talking about? I'm just moving my cursor down. Tell me where in the proof.
I think he's talking about backslash.
Here? Shakti, are you talking about this symbol? This symbol?
Yes, sir.
Yeah.
Yes, sir.
So this is set minus. Okay. I take the so yeah, thank you. Thank you for the question. It's really important. Given x, y subsets of z. So this is purely set theory. X minus y is x in x such that x is not in y, which is the same as x intersection y complement. Does that help, Shakti? So
Yes, sir. Yes, sir. Yes, sir.
yeah,
Yeah,
these are all the elements. So very simply, so elements of S not belonging. Sorry, this is not helpful. S minus S tilde is elements of S not belonging to S tilde. Okay. Now let's come back to this example. So I have a set of 4 vectors whose span is R3, and I'm given a subset of 2 vectors V1 and V2, which is linearly independent. But the span of S tilde is not R3. So I want to, between these two, I want to put in a third set, S prime, which has both properties, that S prime, the span is R3, and S prime is linearly independent. And in fact, I can make 2 choices. I can choose V1, V2, V3, or I can choose V1, V2, V4. This will both be choices of S prime. So S prime, I did not say in I did not say in theorem tilde that there exists a unique S tilde. I just said there is some S tilde. Okay. Okay, now can I resume the lecture? Now we come to the all-important definition, the most important sort of conceptual definitions in linear algebra. Let V be a vector space a set B of vectors is called a basis if B is linearly independent and B, span of B is V. So note that the definition does not say whether the set of vectors is finite. So there are vector spaces, some very interesting vector spaces, in which you cannot find a finite basis. These are called infinite dimensional vector spaces. And so for such vector spaces, you can ask, nonetheless, can you find a subset which has the property that's linearly independent? Note that when I define linear independence of a subset, I did not say that it has to be finite, and such that the subset spans V. And so using transfinite induction, in fact, you can show that you can always find a linearly independent spanning set for any vector space. But to my knowledge, that's not a very useful, I mean, it is very important from the point of view of, I guess, logic and foundations of mathematics, but in actual linear algebra or in practical, relatively down-to-earth mathematics, this is not a very useful fact. I should warn you that when you deal with vector spaces, in infinite dimensional vector spaces with more structure, like Hilbert spaces and so on, you will encounter a term called orthonormal basis for a Hilbert space. And these are linearly independent subsets, but they are not a basis in the sense of a basis that we are talking about now. The difference is that in the case of Hilbert space, an orthonormal basis is one such that every vector in the Hilbert space is a limit of finite linear combinations of the orthonormal basis vectors. But the limit is not a term that we use in algebra. So effectively, we will only talk about finite dimensional vector spaces. Note that I have not talked. So at the moment, so I have not talked about dimension of a vector space, but we know enough now to say whether a vector space has finite dimension or not. A finite dimensional vector space is one which has a finite basis. So let me make that. So even though we have not yet defined the notion of dimension, we can already divide vector spaces into two kinds: a finite basis exists, a finite basis does not exist. And the first type we call finite dimensional, and the second, well, what is can we call infinite dimensional. If in the notes, I did not want to use the word phrase finite dimensional or infinite dimensional before I had defined the notion of dimension. So I have called this finitely generated, these guys finitely generated. That is not very standard terminology in linear algebra, though it's very common in the theory of rings and modules. Okay, very good. So we have defined the notion of basis, and now we come to the heart of the theory, which is dimension. Okay, this is when I need to take a little break. Okay, I'm back. Okay, so now we are going to consider, we will consider finite dimensional vector spaces. So those are, by definition for us, those for which a finite basis exists. There exists first of all, there exists a finite set of non-zero vectors that generates V. And we know from the theorems that we have proved that given such a thing, you can always extract a subset which is both linearly independent and spans V. In other words, you can extract a basis. Okay. So yeah. So maybe I should say that explicitly. Okay. So yeah. So let me just let's wait a bit before we talk about dimension. Okay. So now that we defined the notion of a basis, okay, let's go back to our theorem. The theorem. Forget about theorem tilde. Let's look at theorem. Okay, so this can be this theorem can be reformulated once we have the definition of a basis as follows, i.e., given finite set S such that S equal to V, there exists a basis S tilde contained in S. Okay, so I'm just reformulated the theorem S prime. I've just reformulated the theorem, this theorem, using the definition of a basis. Okay, so now we come to the notion of dimension. So now there are, so let V be a vector space generated by a finite set S. So in other words, these are finite dimensional vector space, right? Okay, so we want to ascribe means give dimension to V. So now there are two ways of doing this. Well, at least two ways. One is to invoke a basic result from matrix theory, which is the way Artin does this, and which is what we will follow. So suddenly the unsatisfactory aspect of this is that so far we have not talked about matrices at all, and suddenly I'm calling on some result from matrix theory. So that is not very satisfactory. On the other hand, this is such a basic fact that you probably encountered it in high school, and so it is okay to use it provided you understand the statement clearly, and the statement will not be in terms of matrices, but it will be a statement about we will see. Okay, and then there is a small additional point, because it will be proved later in the course. We have to be sure that we are not using circular reasoning. Okay. So we have to. So as always, when you use a result that comes later in the development, you have to make sure that when you actually get around to proving that result, you have not used something along the way that follows from the result, so that it becomes a circular reasoning. So you have to be careful about that. That will be clear. Now, but there is also another way of developing the theory, which is more abstract, which I give, I will give in the notes. I don't know if I'll talk about in the class because I don't find it helpful. It's very clever. It's really a nice argument. It's not new. It is there in many linear algebra books. And so we will give that argument also. So what is the, so I'm going to follow this route that uses the following result. We will use the following result. So here is the formulation that you probably know. Given N2 linear homogeneous equations in N1 unknowns, if N1 is bigger than N2, A, if there are more unknowns than equations, there exists a non-trivial solution. So I hope you've encountered a statement like this in high school. Okay, you have systems of linear equations, N2 linear equations, homogeneous, which means that the right hand side is 0, and there are lots of unknowns and very few equations, then you can always find a non-trivial solution. So, I mean, this is how you would have seen this in high school if you've seen it. More formally, so theorem, suppose N1 is bigger than N2, then any linear map T from Rn1 to Rn2 has a non-zero kernel. So in other words, if I have a linear map from the vector space Rn1 to Rn2, where N1 is strictly bigger than N2, then the kernel can't be just the 0 vector. There will be a non-zero vector in the kernel. So we will prove this later when we deal with matrices. So now we can prove the following theorem. Using this, we can prove let V be finitely generated by A. There exists a finite set S such that span of S is V. Then any linearly independent set has at most as many elements in S. Elements in V, sorry. Yes. By the way, so since I have talked about the finite set S that generates V, this linearly independent set need not be a subset of S. All I must, the only thing is that I need S to be finitely generated. Then if I, so so what does this say more explicitly? So, i.e., if B is a basis and S prime in B is linearly independent, then cardinality of S prime is less than or equal to cardinality of B. So this cardinality, number of elements. So this is what the theorem says. So let us leave the proof for later, but corollary. Any two bases have the same cardinality. Right? Because supposing I'm given two bases B and B1 and B2, then this is linearly independent. So cardinality of B1 is less than or equal to cardinality of B2. On the other hand, I can reverse roles and I get cardinality of B2 is less than or equal to cardinality of B1. So they have the same cardinality. So definition, if V is finitely generated, okay, no, sorry. A vector space D is said to be finite dimensional. So now I am redefining finite dimensional if it is finitely generated, in which case its dimension is the cardinality of any basis of D. So note that everything follows from this theorem. This is the master theorem that we have to prove. So forget definitions, everything. You have enough time to go back and stare at the definitions and figure them out. I want to focus on what we have to prove, and so focus. Want to prove if V is finitely generated and B in V is a basis and S tilde in V is linearly independent, then cardinality of S tilde is less than or equal to cardinality of B. This is the master theorem that we have to prove. And we are going to prove this. We will use the following theorem. Any linear map of N1 to Rn2, N1 bigger than N2, has and non-zero kernel. To prove this. Okay, we have not really done a lot, but there have been enough concepts for you to think about. So I'll return to this and finish the business about dimension and so on in the next lecture. So I'm going to stop now. At least stop the lecture now. A number of questions have to be answered. I'll answer them. 1 second.